In crystals, sometimes we need to identify the direction or orientation of a plane. Parallel planes are considered equivalent. The most common approach is to use the intercepts with the x, y, and z axes. If I had a plane that crossed here and here and here, then I could draw a triangle, and essentially the plane including that triangle would be the plane we were talking about. Suppose I have a plane that intercepts the x-axis at 1/2, the y-axis at 1, and doesn't intersect the z-axis. It's parallel to the z-axis, it isn't tilted, so it's never going to touch the z-axis. So the intercepts are 1/2, 1, and doesn't exist. We take the inverses of these. 1/2 is 2, 1/1 is 1, and 1/infinity is 0. If we had any fractions, we would clear them. And if we had any minus signs, we would turn them into overbars. And then this is the notation, the Miller indices for that plane in the crystal. What if one of the intercepts is 0? Then they're all 0 because that would mean the plane was passing through the origin, and this system would fail. Instead, you take a parallel plane. So suppose I had a plane passing through here, 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 and here, and we could move one unit in the y direction and have this going up and right to here. This would be an equivalent plane, and then from here we could try to figure out what the intercepts are. Now, extending the plane, you can see that the y-intercept is 1. The x-intercept would actually not exist. And the z-intercept here, I drew this as going at 45 degrees, so that's going to hit the z-axis at -1. So the intercepts there would be doesn't exist, or infinity, 1 and -1. Invert those, 0, 1, and -1. And the -1 you make overbar, and we put it in parentheses. And there are the Miller indices for that plane.